Welcome to everybody. The topic of my talk is non-supervised classification in the space of SPD matrices. That is symmetric positive definite matrices. I have chosen to start with these Escher's illustrations of the Poincaré disk because, if you will, an important takeaway from my talk is that the methods I am presenting carry through quite easily with very little modification in any space which is of the same kind as this space, meaning a homogeneous Riemannian space of negative curvature. In any case, I would like to start by putting my work into context. So we have at the University of Bordeaux ongoing project of statistical learning in spaces of symmetric positive definite matrices. We are a team of 5 people, meaning 3 lab members and 2 postdocs. And our target applications are remote sensing, radar signal processing, and also neuroscience. We also have ongoing partnerships with the Institute of Mathematics. So Marc Arnaudon, whom you listened to this morning, has talked about fluid mechanics, and also the GIPSA Lab laboratory in Grenoble. Well, the recent most final result of our work is this paper, Riemannian Gaussian distributions on the space of SPD matrices. It is in review. And I would like to ask you to have a look at this paper on arXiv. The link is up there. Well, we deal with several kinds of problems, but the ones I will mention today are dealing with non-supervised learning of probability densities on one, so non-supervised classification in the space of covariance matrices, or SPD matrices, is the first problem. And the second is learning of a probability density. So in terms of applications, we have a database of signals or images. And here I have drawn images, and each image is represented by some kind of covariance matrix with or without a structure. It can be top-list structure, block top-list structure, etc. And this becomes a statistical population of points in this statistical manifold. And then we want, as I said, to estimate its density. And also, we would like to do non-supervised classification. Right. So, admitted, we have taken our database of images or signals. We have translated it into a statistical population of matrices, right? So it's in a statistical manifold, which could be manifold of SPD matrices, of toplets matrices, of toplets, block toplets matrices, etc. And in any case, we begin by equipping this manifold, capital theta, with a Hessian or Fisher metric. So it's a Riemannian metric which is equivalent or equal, in fact, to the Hessian of some function phi, which is model entropy. Right? So in this case, a very important point for our work is with this metric, the manifold capital theta becomes a homogeneous Riemannian space of negative curvature. This mathematical structure is what makes that everything works for us. Now, to give you a very simple example, let's take the most elementary example as a space of 2 by 2 correlation matrices, which I have called baby toplets matrices. Yes? So you have matrices of this kind with a correlation coefficient theta, which is strictly less than 1 in module. Your model entropy is up there, and when you look at the Hessian, your metric, ds2, is the same as the metric of the Poincaré disk, with up there Escher's representation of this metric. So this is to give you an elementary example of the kind of statistical manifold and the kind of metric we have on it. Why is it that we are interested in our work in dealing with this kind of metric? First of all, it gives us all the good mathematical properties that we would like to use. Second, it is related to if you want, a fundamental concept of entropy or event formation through the function phi. Finally, it often leads, we have found, to excellent performance in practical applications. For instance, every year there is a brain-computer interface challenge. You have data from brain-computer interface, which is online. And then people from around the world apply their algorithms to classifying this data. Now, in 2014 and 2015, the first place, meaning the best performance out of anyone who could try, was obtained by someone using a Riemannian metric of this kind. So this means that in practice, there are situations where questions of practical performance of results, applicable results, follow by using this metric. Now I would like to tell you a little bit about our contribution in this field. So just to remind you, we have two problems, which is non-supervised classification and which is also density estimation. Right, so first we have considered the concept of a Riemannian Gaussian distribution. So this is a distribution which depends on exponential of minus square of Riemannian distance, as you can see on the right there. The first question with which we were faced is the computation of this normalization constant. Now we want to compute this normalization constant Z for a general manifold capital theta of matrices, so covariance matrices or covariance matrices with a structure, such as, for instance, Toeplitz structure. Now, this calculation is not easy in general. If we look at the case where capital theta is the space of M times M covariance matrices, first, the Riemannian distance is a very nonlinear function, and second, the integration element, the volume element dv of theta. Well, for example, if we are looking at 20 times 20 matrices, we have 210 integration variables. So integral over 210 variables. That's a lot of variables to integrate upon. Still, by going more deeply into Riemannian geometry, in fact, we were able to obtain this function z of theta. And here it is represented on a log scale. For 10 times 10 matrices and 20 times 20 matrices. So this is in the case where our space is a space of covariance matrices with no additional structure. Of course, we can work with Toeplitz matrices, block Toeplitz matrices, etc. But this is the case of just covariance matrices. So first thing was carrying out this integration. Now, a very important remark is the function z does not depend on theta bar. The distribution has two parameters, theta bar and sigma, and z does not depend on theta bar, and this will be a very useful thing in the understanding the statistical significance of the concept of center of mass. So we have some data, theta 1 to theta n. It is a bunch of statistical descriptors, which we consider to belong to a class or a cluster. And we want to represent this class using maximum likelihood estimates of the parameters theta bar and sigma. Looking at the log likelihood function, thanks to the property that z doesn't depend on theta bar, the log likelihood function separates into something that depends on sigma and something that depends on theta bar only. And this means that maximum likelihood estimation of theta bar reduces to computation of a center of mass. So we have given a statistical significance to the very famous geometric concept of center of mass. Now, with regard to estimation of sigma, it is given by some nonlinear function of the sum of squared distances to the center of mass. In fact, this function we have also, it's a strictly increasing function, so meaning there's a unique solution, there's a unique estimator. And it's also a function which we have tabulated. So in the same way as we have tabulated z of sigma before, this function is also tabulated. So how is this useful to us? In fact, by putting the center of mass within a parametric statistics, parametric inference framework, we can think of things such as hypothesis tests, confidence regions, other such concepts for centers of mass. Now coming to our problems, which are, as I said, density estimation and also non-supervised classification, we were able to rely on mixtures of Riemannian Gaussian distributions. So now that we are able to understand quite properly these Riemannian Gaussian distributions, we can consider finite mixtures with weights omega kappa, which are just positive weights that sum to 1. So in order to estimate the density of some family of statistical descriptors of covariance matrices, we basically do mixture estimation. Now, this is because of our belief that mixture distributions are universal. They can approximate a very, very wide class of probability densities. So by selecting correctly the order of the mixture and then estimating the mixture, we should be able to fit a very general, a virtually any probability density on our statistical manifold. Now, we do the mixture estimation by introducing a, so to speak, Romanian EM algorithm, where we have an E step, which consists in computing conditional membership weights, and then an M step, which for every component of the mixture computes a weighted Riemannian center of mass, theta hat, kappa, and also a corresponding dispersion. Note this is different from the center of mass before because now we have the weights. So this is in terms of density estimation. The other part is classification, right? So I would like to explain, we have this classification rule here, which is optimal Bayesian classification rule. And I would like to explain to you how it works or what it boils down to, basically. So we have a descriptor, theta test, which is here in green, and we want to associate it with a class. Now the class, it has a center of mass, it has a dispersion, theta hat k, sigma hat k, and it also has a weight, omega hat k, right? So intuitively, you want to associate your theta test, you want to associate it to the closest center of mass, right? But imagine hypothetically that it is at the same distance from two centers of mass, right? Which one should we choose? So we have this term over here which says we choose the class which has the smaller dispersion because being close to a less dispersed class is more statistically significant. This term over here, so it says minimize cluster dispersion. So I would go for the class that is here because it's tighter. The first term, it says maximize sample size. So we are choosing the largest weight, meaning the class which has the largest number of elements, right? So also this is in the context of breaking the tie, if you will, but not only choosing the closest center of mass, but choosing the most significant cluster, the cluster that has the best statistical significance. So in the brain-computer interface literature, for example, these algorithms that were applied so successfully to BCI classification, they only relied on this term. So we are hoping that now, for example, in neuroscience, by adding these other terms, we will even improve much better the performance of classification. I have here a simple numerical experiment which is carried out on the vision texture database. So here we have a database of pictures, and basically we want to classify sub-images into the original image from which they were taken. Now, we have our rule, the rule which I called star, the one that I just presented. We have the rule based on the nearest center of mass, and finally, as a benchmark, we have a Wishart classifier. And as you can see, we are able to get in our experiment, the best overall rate of successful classification. We successfully classified 94% of the sub-images into their original image. State of the art, if you will, is the nearest Riemannian center of mass, and that's just behind, it's in second place. Okay, now as an elementary example of the geometry of the space we are working on, I would like to reduce to the case of 2 by 2 symmetric positive definite matrices. So this is a very elementary case, but I'm using it to illustrate all the things that I have said. Looking at a 2 by 2 SPD matrix Y, I decompose it into the product of its determinant, which we write in the form e to the power t, and a unit determinant matrix, z plus x, z minus x, y, y. Now, the constraint of having unit determinant, if you look at it in this way, it's the equation of a hyperboloid, in fact, of the upper nap of a hyperboloid, yes? And indeed, on a hyperboloid of this kind, we can introduce hyperbolic coordinates, r and theta, as you can see there on the left. So z, x, and y are given by hyperbolic coordinates, kind of like with spherical coordinates, but with hyperbolic functions instead of spherical functions. And moreover, when we perform stereographic projection, we obtain a point theta, which is in the unit disk, given by tangent hyperbolic of r over 2 times exponential I theta, which is, belongs to the Poincaré unit disk, right? So this is to show you, again, all the spaces we are working with, they are hyperbolic spaces. They are homogeneous spaces of negative curvature in one way or another. It's very interesting that this construction has a meaning. So our hyperbolic coordinates r and phi, they appear immediately in the spectral decomposition of the matrix Y. So to me, this was a very enjoyable thing to discover, that eigenvalue, eigenvector decomposition is the same as the hyperbolic coordinates. Yeah. Right. So I want to look at the Riemannian geometry of this very simple model. I'm speaking too loud, probably. No? So if we look at this famous affine invariant metric, and we write it in terms of t, r, and phi, the hyperbolic coordinates that I was mentioning just before, we obtain a direct sum of dt squared. Now, t is the log of the determinant, and of the Poincaré disk metric written in polar coordinates. Yeah? So we have this very nice decomposition, and this metric also appears as a Hessian metric if we choose the potential function phi, which is expressed in this way. It's a metric with negative sectional curvature, so this leads to existence and uniqueness of centers of mass. This is a very nice property. And also, it has affine invariance, as the name indicates. So this says we have a Riemannian homogeneous space. And again, this is a very important property to us. Now, first, a homogeneous space means you can go from any point y to any point z by an affine transformation. So any point is obtained from any other point. And a Riemannian homogeneous space means, moreover, these transformations, they preserve the metric. So if you look at a small shape like a triangle, as you move it around, the shape remains the same. Okay, so very quickly, look at our distribution. Remember, it's of the form exponential minus square Riemannian distance. Here we can explicitly compute the normalization function z of sigma. In fact, after some computation in using hyperbolic coordinates, we obtain this expression. So this is z of sigma for 2 times 2 symmetric positive definite matrices. Remember, we tabulated this function for very big matrices like 20 times 20, but in the very special case of 2 times 2, we have the expression written down analytically. And also the homogeneous space property, it gives us the fact that, for instance, when we have some random matrix Y following what we call the Riemannian Gaussian distribution with center of mass Y bar and dispersion sigma, and we apply to it an affine transformation, A dot Y, it just translates the center of mass. It doesn't at all affect the dispersion. So it's a translation property of this family of probability distributions. So we have very concrete understanding of this density of this probability distribution on 2 times 2 SPD matrices, because we even know how to sample from it. If we look at the joint density of T, R, and phi, again, our hyperbolic coordinates, well, we obtain that the three coordinates are independent from each other, with phi being uniformly distributed, t, which is the logarithm of the determinant of the matrix, is normally distributed, and as for r, which is the log of the ratio of eigenvalues, it has this probability distribution over here given by hyperbolic sine of r. So we have this nice little property that the log determinant of the matrix is normally distributed. It has a very simple distribution. It's a normal distribution and independent from all the other aspects of the matrix. So this means we know how to generate samples from this distribution, G, Y bar, sigma. If Y bar is the identity matrix, we use this probability distribution as decomposed above. We generate a uniform angle, a normal T, generate R from this distribution, and then we replace in the spectral decomposition, right? We replace in the spectral decomposition here, and we obtain the matrix Y, which follows this density. In general, of course, if Y bar is different from the identity matrix, we don't have to do any more random number generation. We just generate a matrix following the distribution where the center of mass is Y bar equals I. And we apply an affine transformation, given, for instance, by y bar to the power, the square root of y bar, symmetric square root, and translate to the center of mass that we choose. So this is just an illustration of the concept of Riemannian Gaussian distribution on the very simple case of space of 2 by 2 SPD matrices. As I said at the beginning, we can work with SPD matrices of any size and also of any structure. So Toeplitz structure, block Toeplitz structure, some kind of block structure, in fact. And so with this kind of probability distribution, we have managed to solve problems of density estimation and of non-supervised classification. So I thank you for your attention, and please tell me if you have any questions.
Very interesting talk. Any questions, please?
No, in fact, sorry, I will probably, you need to ask the question again, or do they want you to ask it again, or what? Right. I will answer you anyway. Thank you for your question, first of all. No, there isn't any difficulty. This computation, we could, I mean, given time, I could have shown you exactly the formulas and the algorithm for the case of Toeplitz, block Toeplitz. There's no difficulty. Another interesting extension which our postdoc is working on, don't know where he is. Yes, hello, is to have, in the probability distribution, instead of having d squared, to have just d. So then we work with medians instead of centers of mass. So we have Laplace distribution. So.
Any more questions? I have a small question related to the application that you have showed. Did you apply this yet to other databases? Because Vistex has very homogeneous textures. How does it perform in more general data?
We are currently doing an experiment where, first of all, it has been applied to real data from aerial images. Yeah? And we do have the results for the goodness of fit and all that kind of thing, and they look quite good. I don't have them with me. I haven't studied them, so I don't want to get into detail. Another interesting experiment which we have done is work with what I have just called the Laplace distribution. So instead of d squared, we have d. And to generate outliers. So we take some of our images and we destroy them in part. And we have shown that in that case, we are still able to perform quite well, even with bad data, so to speak, or erroneous data, yeah, given that modification. So this is another thing which we're doing. In practice, what's also very helpful is order selection. So we use some kind of big criterion or other order selection criterion to select the number of components in the mixture. And that helps a lot, in fact. Yeah.
Thank you for the nice talk. I have a small related question concerning your MLE, your maximum likelihood estimator. So, do you have some kind of Riemannian-Kramer-Rao lower bound?
No.
And do you have efficiency?
Right. So Yannick has been asking me this question for 2 years, and I'm not the kind who likes to do long calculations. Like, I'm hoping that one day or another we are going to discover, for some good reason, what is the Kramer-Rao lower bound, and just find it out. But yeah, so it's a hot topic. It is. So, and in my opinion, actually, this is efficient. I think it is efficient. It does achieve Kramer-Rao lower bound because of the symmetry and the problem. But I haven't carried out the computation. It's in progress. Yeah. Thank you.